Okay, hi everyone. Welcome to the October seminar. This month, we've got Charmaine Franklin from the Bureau of Meteorology speaking about urban scale fine modeling, and this is down to the very, very fine. So, Dr. Charmaine Franklin is a principal research scientist at the Bureau of Meteorology, where she leads the research program's atmospheric modeling team. She has expertise in developing models across all states, from direct numerical simulations, large AD models, city-scale numerical weather prediction systems, all the way through to coupled climate models, and with a focus on representation of clouds and convection. And prior to working at the Bureau, she's worked at McGill University and CSIRO, and she's currently participating in several international research committees, including the Scientific Steering Committee of the WMO-sponsored Paris 2024 Olympics Research Demonstration Project, and the World Weather Research Program Nowcasting and Mesoscale Research Working Group. Also, the UN Partnership Regional Modeling Governance Group. So, thank you very much, Charmaine, for presenting, and take it away.
Thanks very much, Nathan. So good morning, everyone. So today I'm going to talk about some of the research happening at the Bureau and elsewhere around developing our urban fine-scale weather models. So Australia is one of the most urbanised countries in the world, with 90% of the population living in urban areas. And given the high density of people in urban areas and their dependence on infrastructure, urban weather effects have important impacts on public health and safety, transportation, energy demand, and a number of other things such as urban design. And the types of weather events that urban populations are particularly vulnerable to includes heat waves, urban thunderstorms and floods, extreme winds, fog, air quality, and bushfires. And with the advances in computing, we're working on improving the Bureau's urban weather information by expanding our current numerical weather prediction capabilities to include these very high resolution 100-metre scale models. And while predicting some of these urban hazards does require coupling to other models, like for example, for air quality, we need to couple to a chemistry model. For urban floods, we need to couple to a hydrology model. Good performance of these coupled environmental prediction models does require a good underlying performance of the urban meteorology. And so in this presentation, I'm going to go through some of the research challenges for these very high resolution 100-metre scale models, and talk about some of the research happening around the world to improve the representation of urban meteorology in our simulations. So starting off here, we're looking at the scale of the surface heterogeneities. So this is an image of Sydney, and you can see the left scale 3 kilometres. So if we look at some of those different surface properties and the surface heterogeneity, we can see that the scale of those different surface features usually occurs on a scale of about a couple of kilometres. And the Bureau's current high resolution modelling system has a horizontal grid length of 1.5 kilometres. So that means that access city system is not able to accurately represent the different weather conditions across the city. And as the demand for more localised weather and climate information grows, we're really looking to our next generation of models to provide guidance at the neighbourhood scale. And these 1.5 kilometre models are not able to resolve conditions across the city. So we really need higher resolution models. So if we zoom in to a closer area of Sydney and now overlay that with a 100-metre grid, we can see that to be able to resolve the conditions across the city, we do really need to push down to these 100-metre type scales. And at this resolution, the models are more able to accurately represent the effects of urbanisation on local weather, and also they're able to represent better some of the phenomena like thunderstorms. And so when we push down to the 100-metre type scales, we do see improvements in many things, and that comes about due to two main things. So the first of that is due to this finer resolution and the better representation of the surface characterisation. And that's due to both the topography and also representing the conditions across cities more accurately, like we can see from these building height maps on the right-hand side here. So the difference between the topography for a 1.5 kilometre model and a 100-metre model is shown on the left there. And you can see that greater detail at high resolution, we're capturing the hills and the valleys more accurately. And so that produces better simulations of weather that is really strongly topography forced, for example, fog. The more detailed urban characterisation at the 100-metre model produces more accurate predictions of conditions across cities. It allows us to resolve the city in our simulations. And it's really these 100-metre simulations, sorry. So the one aspect is this higher resolution surface characterisation. The other area of the 100-metre scale models that give us improvements is around the representation of turbulence. And here I'm trying to illustrate that by looking at the vertical velocity fields for 3 different resolution simulations. So we have a 1.5 kilometre run on the left, 400 metres in the middle, 400 metres on the right. So you can see for the 1.5 kilometre run, you can see the updraft and downdraft represented here. They're really quite weak and broad structures. At 400 metres, we have more detail being represented and stronger updrafts and downdrafts. But you can see at 100 metres, things look quite different in the vertical velocity field. You can see these really small structures of these drafts and downdrafts being represented. And this is an indication that aspects of the turbulence are now starting to be resolved in the 100-metre simulation. And that better representation of turbulence impacts things like how the model simulates convection and other things that are dependent, like, for example, an entrainment into the boundary layer. So here I'm showing sort of where the urban scale models sit within the regime of our sort of current models. And as the resolution is increasing with global models, it's also increasing for our regional models and our urban models. But as we reduce the grid length and increase the resolution, these runs become quite expensive, and so we need to reduce the domain size, which is shown on the right-hand side here. So within the regimes, we do encounter these grey zones, and these grey zones are where our current parameterisations are really not designed to work at these scales. And that's because the length scales of these features are similar to the grid spacing used in the models. So the moist convection grey zone affects our regional modelling systems that have kilometre scale grid spacings. Our urban models running at the 100-metre scale are affected by the turbulence grey zone for the atmospheric model and the building grey zone for the urban surface scheme. So the higher resolution of our urban scale models enables improved representation of many important meteorological phenomena, as well as these better resolved urban areas. So those things are really beneficial. However, the grey zones in the simulations do present a number of challenges that I'm going to talk about. So here I've put together a table of the benefits and challenges of running 100-metre scale models. So some of the aspects come about due to high resolution of atmospheric model in this column. Some come about due to high resolution on the representation of the surface, they're shown in this column, and some come about due to a combination of both of those things. So the high resolution atmospheric model gives us benefits in the representation of the convective boundary layer, convection, sea breezes, and we're now able to explicitly represent tornadoes in the model. The surface characterisation, we see improvements in orographic rain coming from that better representation of the topography and also the urban temperature distribution because we're resolving conditions across the city. Other things we see improvements are in the forecast for fog, air quality and dispersion, and winds and gusts, particularly in urban areas. The challenges come about due to this, the fact that we're sitting much in the grey zone and the building grey zone, which I'll talk a little bit about. Convection is also a challenge, even though it's also a benefit. We still do see aspects of convection in the model that need to be improved. We also have uncertainties and questions how we represent the anthropogenic fluxes of heat and moisture at these 100-metre scales. And we do need to consider how urban heterogeneity, both in the vertical and the horizontal, starts to impact on the flow. Other aspects we need to start thinking about are how we deal with the spin-up effects from the boundaries, predictability aspects when we're running at these very high resolutions, and also how we deal with the affordability of these 100-metre simulations because they are very expensive models to run. So in the presentation, I'm going to go through and illustrate some of these benefits and challenges of our 100-metre scale modelling. So first thing I want to talk about is the turbulence grey zone. So this has also been termed terra incognita, and it's a way of describing a numerical regime where the atmospheric motions on the model grid are starting to become partially resolved. And so this figure is showing the daytime convective boundary layer, where we have thermally driven motions creating these eddies of rising and falling motion. And those eddies act to deepen the boundary layer. So the top is a representation of this for a coarse resolution model. And in that case, you can see that the grid boxes are large enough, such that there's a number of these in a grid box. When we look at this for a high down the bottom, you can see that now we have at most one of these eddies being contained in these grid boxes. So boundary layer schemes in models, so the sort of classic 1D schemes that we use in our kilometre scale and coarser resolution models, are really developed to represent the average effects of many eddies. So they're really designed to work in that top situation there. And because when we run that scheme at higher resolution, there aren't enough eddies to properly sample the average behaviour. So we see that the turbulent scheme really doesn't work very well, and it fails to represent the effects of that turbulent motion. And the impact of that is really, we see delayed onset of resolved motions. And I'll show you an example of what that sort of looks like in our simulations in a second. I firstly just wanted to talk about one of the ways that we can deal with the turbulence grey zone in the unified model. So people at the Met Office, Ian Bootle in particular, has developed what's called a blended turbulence scheme. So there are two different turbulence schemes in the model. There's the 1D sort of kind of classic way of representing the turbulence in our kilometre scale and coarser resolution models. And in that case, all of the turbulence is under-resolved. Works well for those kilometre scale and larger scale models. We also have another scheme available in the model that's called a Smagorinsky scheme. This is a scheme that's used in large eddy simulations and typically sort of used when you run your model at the grid scale's got about tens of metres, where the large eddy box are resolved, and actually that's scale turbulence that needs to be represented, the effects of that by that Smagorinsky scheme. So we have this blended scheme in the UM that actually uses both of schemes, and it blends together the effects of those. And the blending is based on a weighted average of the two approaches, where the weighting is dependent on the turbulent length scale, which is the meteorological regime, or if you like, the boundary layer height, and the grid length. So to show you sort of what it looks like when you run a model at 100 metres with those different turbulent schemes, these are 100 metre simulations from Ian Bootle at the Met Office, and here we're looking at plots of the vertical velocity. So when we run that scale where, if you like, that seamless blended scheme, it looks very similar to when we use the 3D Smagorinsky scheme, which is the scheme designed for very high resolution large eddy simulations. You can see we have the inflow coming in here, and we have these roll-like structures forming. As the turbulence starts to be developed and resolved, those roll-like structures break down into these smaller scale updrafts and downdrafts. And we see that it looks very, very similar when we use those two, the blended and the 3D Smagorinsky scheme. Looks very different though when we run the model at 100 metres with the 1D boundary layer scheme. You can see almost no resolved turbulence here. We have very weak vertical velocities, and we see hardly any of these rock structures forming. So really, running 100 metre simulations, we need to be running with turbulent schemes that really are designed to work at these scales. And while the seamless or this grey zone blended approach does look pretty good, it's not perfect. And we really see the limitations of that when we compare it to 10 metre scale large eddy simulations or the developing convective boundary layer. And in that case, we see the small value of the mixing height when the convective boundary layer is very shallow. Actually, the turbulence representation by that seamless scheme in the model makes the energy diffuse too quickly. And we see a delay in the development of that convective boundary layer. So we really need to be developing these scale-aware turbulent schemes, particularly for these grey zones, these 100-metre simulations. So moving on, also when we're modelling at the 100-metre scales, it means that we are not resolving the effects of individual buildings, but nor are we representing many buildings per grid box. And this means that we are in what's called the building grey zone, where just as in the same way as for the turbulence, the urban canopy schemes that we use are really designed by assuming that there are many buildings per grid box, and we represent the collective effects of all of those buildings. Urban canopy schemes are often developed by assuming a homogeneous, moderately low street canyons, and there are challenges in how we represent the heterogeneity of the urban areas, both in terms of the vertical and in the horizontal. For example, how do we include the effects of sort of tall buildings that we see from the building resolving simulations? They modify the flow over quite large distances. We also need to think about urban vegetation and how to account for street trees on the momentum and scalar exchanges within the street canyons. The current approach in the UM to deal with this is we apply a small adjustment to parameters. But when we push down to the 100-metre scales, we really need to be explicitly including the effects of the trees on the buildings. Another complication is the representation of the anthropogenic fluxes of heat and moisture. So there's a number of different ways that you can represent these effects in models, but we're often limited by the lack of high resolution data that's needed to define these sources at the 100-metre scale. I thought it might be useful just to briefly introduce the urban surface scheme that we use in the model. It's called MORUSES. It's the Met Office Reading Urban Surface Exchange Scheme. It's a single layer urban canopy scheme that's coupled to the lowest model layer. It represents 2D street canyons with separate tiles for the roofs and canyons, and it accounts for the in-canyon radiative exchange. The canyon dimensions and roof thickness is dependent on the local urban morphology, and it's that building geometry that determines the roughness lengths for momentum and scalar exchanges. So there is a method in MORUSES to deal with the anthropogenic fluxes, and the way that works is it takes daily sources for each grid box and each season and converts those into diagonally varying an anthropogenic heat source. But ideally, we really want a more sophisticated approach that links the forcing to the temperature so that we can capture things like, for example, the impact of everyone turning on their air conditioning when we hit a particular temperature threshold. And there is a lot of discussion happening at the Met Office at the moment around developing the urban scheme. So developing a more sophisticated representation of the anthropogenic fluxes is one thing. They're also looking at using a distributed form drag in the short term as a sort of intermediate step between developing their next urban scheme, which will be a vertically distributed scheme. So I'm just going to move on now and start looking at sort of the challenge here of spin up from the boundaries, domain size, and affordability. So we often see these large-scale structures at the inflow boundaries on our sort of 100-metre scale models, and you can see these sort of structures here, here and here. So they look quite unrealistic. And this is sort of where it's taking quite a bit of time for the small-scale structures and features to develop and for the turbulence to be represented. And one way of dealing with this is to simply make our domain bigger so that our region of interest is well away from the boundaries. But these 100-metre models are very expensive. And to give you an idea about how expensive they are, if we run a 100-metre model for the same domain as for a 1.5-kilometre model, the 100-metre model is 9,000 times more computationally expensive. So simply just creating a larger domain is often sort of not a feasible option. The other ways that we can deal with this spin-up is to use what's called a variable resolution grid. And so the grid boxes in that case are larger in the outer region of the grid, and we just keep that very high 100-metre resolution in the inner region of interest. So that enables us to run a larger domain at a lower cost to avoid these spin-up effects sort of in our centre region of interest. An alternative approach is to inject noise into the model via the boundaries, and that can help to spin up the turbulence more quickly, but we also sometimes see some adverse effects from that as well. But ultimately, we need a large enough domain to allow the representation of important mesoscale interactions, the important interactions between the mesoscale and the urban scales. And particularly for the simulation of convection, we do see that we need to have a large enough domain to be able to get those interactions happening to produce good simulations of convection at the 100-metre scale. So here we kind of just want to talk a little bit about uncertainties and predictability. And so while running at these very high resolutions presents many advantages, the smaller grid sizes do create a challenge in terms of predictability. So small scale forecast errors grow quickly, and because convective processes are non-linear, they're strongly affected by uncertainties. So the approach to deal with this is to create an ensemble of possible numerical forecasts, and we create our ensemble by perturbing both the initial and boundary conditions, as well as some of the physics parameters that are quite uncertain. And to illustrate sort of why we want to be running ensembles, particularly for convection cases, is kind of illustrated in these figures down the bottom. So this is the radar image of a school line impacting Darwin. And this is the simulated radar reflectivity for 3 ensemble members from a 400-metre ensemble simulation. So you can see that all of these simulations in these red colours have deep convection and heavy rainfall. Only in the middle that actually produces this well-organised scoreline. And that's important for forecasters. These different types of convection really determine what types of hazards you might want to be preparing warnings for. So scorelines in particular are often associated with very strong and damaging wind gusts. So providing an ensemble helps quantify the forecast uncertainty and allows the users of the model guidance to kind of have some degree of confidence in how much they should be weighing in on any particular forecast. But one of the other aspects is with these high resolution models and around the predictability limits is we do need to avoid evaluating and verifying models and providing model guidance on unpredictable scales. So to show a couple of examples of what I mean by that, here we're looking at the benefit of running ensembles as compared to a single deterministic forecast for a heavy rainfall event that occurred over Adelaide. So in this case, we use neighbourhood methods to evaluate the model, because if you were just used to use a full grid point as compared to a grid point, the model is wrong. It has no skill. Actually, when we look at the larger scale regions, we do see now sometimes very high skill from our high resolution simulations. So this figure here is called the Brier skill score, and this score here is being used to show how much more skillful our rainfall forecast from an ensemble is compared to just a single control forecast. So we have different resolution ensembles here. So black line is the 1.5 kilometre system, blue the 400 metre, and red the 100 metre. So a skill score above 0 means that the ensemble is more skillful. You can see that for all the precipitation thresholds, all these scores are above 0. But you can also see that the benefit of the ensemble actually increases as the rainfall increases. So the skill score is higher for these very heavy rainfall events. So we really do see that particularly for convection and for heavy rainfall, running an ensemble of simulations is quite important. And this is an example of sort of providing, if you like, model output and information to users using sort of neighbourhood approaches. So these are maps of the probability exceedance for daily rainfall over Darwin. So this is the top lines are for 5 millimetres per day, and down the bottom here is 20 millimetres per day. So these figures on the left are a grid point ensemble probability, and so they show the likelihood of an event occurring at the grid scale. And basically, really what we want to see are dark blue colours, high probability, covering these regions where the radar observed rainfall, regions in grey. So we have high probabilities occurring at Tiwi Islands, which is good. But when we start to look at these sort of heavy rainfall events, so this is one impacting the mainland of Darwin, we don't see a lot of useful information coming out of the ensemble when we provide a grid point probability. However, on the right, where we are providing what's called a neighbourhood maximum ensemble probability, which is giving us information about the likelihood of an event occurring at spatial scales larger than the grid scale. Now we can see much more useful information. So very high probabilities coming from the Tiwi Islands for both of those rainfall thresholds. And you can also see now useful information coming from that convective event over the mainland as well. So those ensemble probabilities are really more useful when we use this neighbourhood approach. And really it's because that approach recognises the limited small scale predictability. So I'm going to move on now and talk a bit about how convection is represented in these sub-kilometre models. So this is something that I've worked quite a bit on over the past few years. So these figures are showing what a tropical scoreline looks like in the model when we simulate it at 3 different lengths, 1.5 kilometres, 400 metres and 100 metres. So this is sort of cross sections through the storm, and the coloured contours here are the simulated radar reflectivity. So looking at the 1.5 kilometre simulation, you can see that the convections are quite large, circular. There's a representation of air cloud happening. And it's really telling us that the convection is under resolved. So we're very much sitting in that convection grey zone. The model struggles to simulate big convective storms sometimes. At 400 metres, we see a much better representation. of the storm. We have the convection being aligned along the wind, and we can see this generation of this really extensive trailing stratiform cloud. Looks very similar to the observations. At 100 metres, it looks more similar to the 400 metre simulation, but now you can sort of see these very small convective cores being represented in the model. Actually, the area of the storm and this anvil cloud is actually being reduced in the 100 metre simulation compared to the 400 metre simulation, and that looks less like the observations in this case. And I think the reason behind that is the different scales and updrafts being represented, and the fact that we don't have this turbulence scheme that's primarily being developed for handling turbulence in the turbulence grey zone at 100 metres. So this illustrates what the different updrafts kind of look like as we change the resolution of the model. So here we're looking at the outlines here in black are the updraft areas defined as being greater than 1 metre per second. So the average size of these updraft areas at 1.5 kilometre simulation is 75 kilometres squared, so really quite large. 17 kilometres squared for the 400 metre, and really small, only 4 kilometres squared at 100 metres. But I think when we look at total area being covered by those updrafts, we actually see that it's smallest in 100 metre simulation. And I think the reason for that is because we're simulating these very small updrafts, and the turbulence being represented in the model actually isn't training too much, and it's limiting the ability of the 100 metre model to sort of upscale and develop that convection. Looking at a similar thing now, but for a different case. So these are cases where I've run different ensemble resolution systems for the tornado outbreak case that happened in South Australia in 2016. So if we compare the convection for the ensemble members from, this is again the simulated radar reflectivity at 1.5 kilometres and 400 metres, and compare that to the observations here on the left, we can see that at 400 metres we're better resolving the convection. It has a much more realistic structure and more of that lighter stratiform rainfall, so there's lower reflectivities. 100 metres looks very similar to the 400 metre run, but there's a lot of really small scale detail in here that I'll show you in a little bit more detail. The other thing to note from these images are when we look down the panel and look at the different performance happening from those different ensemble members, we actually see really good agreement in this case, which is quite different to that previous case that I showed you. And so that gives users of this model output really good confidence in the guidance that they're getting from the model. It kind of tells you that there really is something like this likely to happen in reality. So focusing in on some of those more detailed representation of the convection and comparing to the radar observations at this time. So at this time we did actually have a tornado observed, and this is the hook echo that you can see on the radar image here. So you can see a presentation of kind of that hook echo in the 1.5 kilometre simulation, but you can see that the convection is quite large. We're missing a lot of the convection. We're also missing a lot of that lower reflectivity stratiform lighter rain in the 1.5 kilometre simulation. 400 metres looks a lot better. We have more of the convection occurring and a lot more of those lower reflectivity lighter rainfall regions. 100 metres we see some really nice features here. So we see these rain bands forming that we see also in the observations. We can also sort of see evidence of a hook echo, and we can also start to see some of these really detailed structures like this vortex here. So at 100 metres, the model should be able to represent explicitly some of these tornado-like vortices. And actually for this case, we do see the model producing these tornadoes, and I'm going to show you what they look like. So here we're looking at an animation of the simulated radar reflectivity and winds at 10 metres above the surface. And what I want you to do is look at this convergence line here, and you can see these vortices spinning up on that convergence line. And that's the tornadoes in the simulation. So if I just zoom into that region. So again, here we're looking at the radar reflectivity at 10 metres above the surface. And these black lines here are now representing the vertical vorticity, so giving you the measure of rotation and really indicating the presence of that tornado. Just let's play through again. So here we see the tornado spinning up. It's at its strongest around about now, and then it starts to dissipate. The other thing to notice is other secondary vortices spinning up behind him. And so in this case, there were 7 observed tornadoes, and the fact that the model is able to simulate multiple vortices is actually quite an exciting result. So we have a little bit of a look at the structure of these vortices. So the minimum vertical vorticity was about minus 0.4. That strongest vortex lasted at that strength for about 15 minutes, and it had a diameter of 600 metres. And 600 metres is really the smallest scale diameter that we can expect a 100 metre equivalent model to simulate. If you look at the wind speeds associated with that vortex, which are these figures on the right here, we can see that vortex had a maximum wind speed about 50 metres per second, and that's equivalent to an EF2 strength tornado. And actually that was the strongest tornado observed for this case. You can also see that these other secondary vortices behind here had wind speeds that are equivalent to vortices of an EF0 and EF1 strength. Again, that was similar to what was observed. So while it's really great to see the model able to represent these vortices, what we really want to assess is whether the model is producing these vortices for the right reasons. Are the types of features that we expect to see in tornadic supercells actually present in this 100-metre simulation? So I'm going to take this cross-section here to have a look at what sort of features are being simulated by the model. Okay, so here we have a cross-section. The colour contours here are the radar reflectivities, and the black lines are the vertical velocities, the updrafts being represented by the solid lines, downdrafts by the dashed lines. And you can see the outline of the tornado shown here. This is sort of the outline of that vertical vorticity field. And we want to compare this to kind of this image that we kind of get to see, this classic image of a tornadic supercell here. So we often see this flanking line, and we see this in the simulations where we see this flanking line in the precipitation-free cloud base. We see this very strong tilted updraft here in this simulation. Behind here in the downdraft region, we have these high reflectivities here, sort of 60 dBz, and that's really indicating the presence of heavy rain and hail in that downdraft region behind the tornado. And again, that's exactly what we expect to see. So this kind of looks like the model is doing a pretty good job here. If we now have a look at some of the aspects around the formation of the mesocyclone and the tornado. So again, this is a schematic, sort of what we might want to see. And this is a cross-section, which is the same cross-section as before. So we have the wind vectors on here. The coloured colours behind here is the potential temperature field. And this orange colour here is the vertical vorticity, showing you the location of the tornado. So we do have this inflow coming in, it's sheared, and we have this tilting up of that sheared wind in the vertical. And that's really what gives rise to that formation of the rotating updraft of the mesocyclone. In this downdraft region, we can see that now the temperature gradient is quite pronounced in the vertical. And what that means is for the inflow coming in behind here, the vertical gradient of the temperature spins up horizontally rotating air. And as that horizontally rotating air flows in and meets that strong updraft, it gets tilted into the vertical. And that horizontal vorticity then gets tilted up and becomes vertical vorticity, and that's really what is behind the generation of the tornado. So the simulation again looks pretty good. A couple of other things to look at here. Here we're looking at plan views through 140 metre altitude. So the black lines here are the pressure field. We have the wind vectors, and the different colours are the vertical vorticity on the left, potential temperature in the middle, and vertical velocity on the right. So you can see this hotspot in the vertical vorticity is the location of our tornado there. And you can see we have this strong band of vertical vorticity extending down here. And this is really the region where we have the intersection of the forward flank gust front and the rear flank gust front here. And when we look at the intersection across the gust front here, we can see a temperature difference of about 2 to 3 Kelvin. And that's really what we would expect to see given the different origin of the air masses in that case. So that was pretty good. And looking at the vertical velocity field, we see this really nice horseshoe-shaped updraft. And we can see this downdraft, this rear flank downdraft wrapping around the updraft. And it's really at that intersection of the updraft and downdraft where we see the location of the tornado. And one of the things that we can do with these 100-metre models when we have a good simulation of, for example, this tornado, is start to look at some of the processes that might be important in the formation and the evolution of these vortices. So I've started to do this by looking at some of the impacts of the microphysical processes. So in this region in the downdraft where we have this heavy rain and hail, we expect that the cooling associated with some of those microphysical processes are really key in the tornado genesis process. So what I've done is I've run a couple of simulations where I remove the latent heating from these processes and look at what the impact of that is on the formation of these tornado-like vortices. So these are time series of the mean sea level pressure at the top and the 10-metre vertical vortice at the bottom. So the control line in black here is that simulation I showed before, and you can see this drop in the mean sea level pressure here is where we see the formation of that EF2 strength vortex. So we look at the blue line first. So this is where we remove any of the cooling associated with the evaporating rain. So we can see that that delays the formation of that strong vortex by about 20 minutes, but actually it creates a stronger vortex. So we have an even further drop in the mean sea level pressure in that case. Looking at the effect of the melting ice, which is the red line. So we can see now that, again, we slightly delay the formation of that vortex. It still is about the same strength, but it lasts for a shorter period of time. The interesting thing about that simulation, though, is that the line doesn't produce any of those secondary vortices. So it actually looks like the cooling that's coming from the melting of ice is quite an important process in the simulations. So I'm going to work some more on this. It's really work in progress to understand more about this particular case and what the processes were regarding tornado genesis. And the aim of that is really to help understand more about the processes to help build better warning systems, hopefully. The kind of final thing that I wanted to talk about is a big international project that's happening at the moment called the Paris 2024 Olympics Research Demonstration Project. The aim of this project is to advance our research on the future weather forecasting systems at 100-metre resolution for urban areas. And the reason why we're doing this work and why it's supported by the WMO is because these systems are really going to pre-configure the numerical weather prediction systems sort of on the timescale of about 2030. So this project is being organised by Valérie Masson at Météo France. There's 9 different modelling groups involved in this from around the world, including many of the big Met centres like the Met Office, NCAR, NOAA, Environment Canada, KNMA, and a number of others. So we're really involved in this project in the modelling work, but there are a number of other aspects happening for this project. So the big sort of science questions are firstly around nowcasting and numerical weather prediction in cities at 100-metre resolution, high resolution thunderstorm nowcasting, both for Ensemble, so probabilistic nowcasting, as well as deterministic, looking at effects of urban heat islands and air quality in cities. There's also a focus on looking at 100-metre scale modelling for coastal sites. So the sailing for the 2024 Olympics is going to happen at Marseille, and there's really complex sea breezes there. And so this is actually particularly interesting for us at the Bureau, given that most of the Australian cities, of course, are coastal cities. Other science questions are around big data, non-conventional data and their uses, and also how to deliver tailored weather, climate and environmental information at these infra-urban resolutions. So for the modelling work, there's really 3 main stages for this project. The first has started and is currently ongoing, and that's running our models at 100-metre resolution and intercomparing the models for 2 extreme weather cases. The next step is going to be running some simulations and evaluating them from an intensive observational campaign that will happen in Paris in July next year. It's really fantastic to be involved in this program to be able to get the observations. So we're going to have really high density surface obs, lots of radiosondes and potentially up to 6 LiDARs working across the city. Excuse me. And the aim of this really is, from the first and second of these activities, is we're going to evaluate and hopefully improve our models from what we're running today, so that they'll be ready to do this real-time forecasting for the Paris 2024 Olympics to support the weather forecasting during that event. So science questions for the modelling activities is firstly analysing and improving our models, comparing between models to look at what errors are common, and also comparing with large eddy simulations, so these 10-metre scale models that a number of the modelling groups are running. It's going to be fantastic to have those output to compare to our models. Science questions just around using the observations and the models to better understand the urban boundary layer and the convective processes in the urban environment, understanding how the boundary layer behaviour and its characteristics and also convection depend on our representation of the urban canopy and the subgrid turbulence. Looking at different methods to compute the urban descriptive data, analysing the impact of the detail of that data on our simulation, and also looking at the impact of how we represent the anthropogenic fluxes over Paris. And then finally linking with operations, looking at the ability of our current kilometre scale NWP systems to provide useful information on extreme heat and heavy rain in urban areas, and then looking at the benefits of now introducing these 100-metre models. So 100-metre models are super expensive, so we really do want to make sure that if we're going to invest a lot of compute in running them, that they really are beneficial for the forecasting in urban areas. So I do just want to show you some early results for these two intercomparison cases. So there's two cases. One is the heat wave from July 2019, and the second case is a thunderstorm and flooding case from July 2017. So Vinod Kumar at the Bureau is working on this and has been running the Paris heatwave case. And one of the things he's been looking at is looking at how the representation, the complexity of the urban scheme actually, how that sort of manifests in better or worse simulations for this Paris heatwave. So here we're looking at the surface temperature from two simulations. Simulation on the left uses a very simple slab urban surface scheme. The simulation on the right uses the much more sophisticated MORUSES scheme that I spoke briefly about before. Whereas here, for the MORUSES setup, we're not using Paris-specific data, but instead using the default empirical functions to derive the urban morphology. And so if you compare those two surface temperature fields from those different simulations, you can see that the distribution of heat across the city looks pretty similar, but actually there are some differences there in the magnitude of the temperatures being represented. So to look at that in a bit more detail, Vinod has compared to some observations, and we're looking at here a time series of the 1.5 metre temperature for two different locations in Paris. So this top figure here is for this central Paris region. This lower location here is further sort of out of the city a little bit to the west. So the black line here are the observations. The blue line is the simulation that uses MORUSES, the more sophisticated urban scheme. The red line is the simulation using the very simple slab urban scheme. So you can see that both of the simulations sort of fail to produce the correct amount of cooling here. We can see a better representation from that more complex urban surface scheme. We can also see a better representation of the heat in the morning from the blue line, that more complex scheme. And also for this location further to the west, we also see that better representation when we run that more complex scheme with the cooling of the city temperatures as well. So even with running MORUSES with sort of default, if you like, so non-Paris specific urban morphology data, we do see benefits to running a more sophisticated urban scheme. And Vinod's been doing a lot of work actually to merge the ancillaries and provide kind of take into consideration this third-party data that gives us really good representation of the characteristics of the Paris cities and the buildings. This is far from trivial work, as people in CLEX who have generated these files would know. So this is sort of what Paris looks like, and this is the building heights when we use the default empirical information here. So we really see no variability of the building heights across the city. It looks very different to this data that's been provided as part of the RDP, where we see taller buildings in the centre of Paris and a lot of variability across the city. But it's far from straightforward how you merge these data sets together, but Vinod has done a fantastic job in producing these ancillary files now. So we now have this merged data set that we can use with MORUSES and see what the impact of that is on that representation of that heatwave case. So that's for the building heights, and we see a similar thing when we look at the height to width ratio. Again, using the default information from the we see really very limited variability and no sort of representation of that higher ratio associated with the taller buildings in the centre of Paris. The other case I just briefly wanted to show you is the Paris thunderstorm case that Kirsty Hanley from the Met Office has been running. So these are the observations of the rainfall for this case. And Kirsty's run different resolution simulations, so 1.5 kilometres, 300 metres and 100 metres. And she's used different forcing for the model. So the top line here is when you use the global to provide the initial conditions and boundary conditions. And the lower panel here is when you use ECMWF to provide that forcing. So you can see when you look across the panels, in both cases, we can see a much better representation of the convection in sub-kilometre simulations as compared to the kilometre scale models. So better representing convection, and we really do sort of see that in the representation of this convective case. You can also see when you compare top line to the bottom line that there is quite a bit of sensitivity around how you drive the model and whether you use the global model or ECMWF. And sort of putting that information together here, I can produce this time series of the domain average rain rate. And you can see for the sort of purple and pink lines here, so these are sub-kilometre runs driven by ECMWF. We actually see that convection initiates earlier in those simulations. We don't produce as much rainfall. Comparing that sub-kilometre simulations from the which is this red and cyan line here. So convection is initiated a little bit later and actually builds and produces these larger rain rates, which for this case actually looks a bit better. But Kirsty's sort of conclusions so far are that we do see benefits when we run the model at these sub-kilometre scales. There is really strong sensitivity to the driving model for this case. And ideally for convective cases, like for this case, we do need to use an ensemble to disentangle the predictability issues. So that brings me to my summary. So urban fine scale weather modelling at the 100 metre scale can provide better guidance for urban weather hazards when we compare that to kilometre scale models. And that's really due to that better representation of both the surface characteristics and also the turbulence. However, we do need to be careful about how we evaluate and verify and also use the model output due to that limited small scale predictability. So it's pretty exciting when you see that 100 metre models can simulate tornadic supercells, and that really gives potential for longer lead times of tornado warnings and the identification of these enhanced risk regions. So currently tornado warnings are based on observations when we see signatures in the radar fields, and that doesn't give you very long, so you've only got sort of 30 to 60 minutes to issue a warning. Whereas if we can get our models to produce good tornado simulations, then obviously we can increase that warning by significantly to sort of a day. So advancing the provision of urban weather and climate information is a WMO priority area, and they're supporting a number of projects to further research on these 100 metre models, like for example the Paris Olympics research demonstration project. And I do want to say that the research on the processes and the model developments really are integral components of producing reliable and accurate forecast products and services for urban regions. That's going to be one of our focus areas in the research program at the Bureau over the coming years as we develop the Bureau's first urban scale numerical weather prediction system. And finally, future research. So there really is a big need to develop these scale-aware parameterizations of subgrid processes, both for turbulence and also for the urban areas. So for the urban areas, how can we characterise the attributes of these really highly complex geometries with this scale adaptive and spatially varying approach? How do we take into consideration urban vegetation and how it interacts with the buildings and also the anthropogenic effects? Looking at trying to better represent convection in our 100 metre models. So we see some things improve, but not everything. And that may be related to both the turbulence scheme, but also the microphysics and potentially the inclusion of aerosol effects, those higher aerosol loadings in urban areas. So going to be working on the Paris RDP. There's another of other field campaigns happening internationally too. So if we can get our hands on those observations, that's a really great way for us to evaluate and develop our models. We do need to keep thinking about affordability and how we can improve that by optimisation. Also, a lot of work I think needs to be done around understanding the trade-offs around domain size and resolution. And then finally, once we've done all of that and we have the optimal urban scale model, we can then look to coupling with other models like driving air quality models and hydrological models as well. And so thank you very much. And the last thing I want to say actually is I just want to give a plug for the Bureau's annual R&D workshop that's going to be happening on the 8th to the 11th of November. So this year's workshop, there will be an urban session. We have a really exciting lineup of speakers, including Melissa Hart and Sue Grimmond. So if you're interested in having a look at the draft program, there's information on this website and you can also register here. So thanks very much, everyone.
Thank you. Thanks Thanks, Charmaine. That was fascinating. Fascinating to hear sort of the leading edge of numerical weather prediction in terms of resolution and some of the case studies. Yes, so I invite everyone to ask your questions either in the chat or in the Q&A section. We've actually got a few in the chat already. So perhaps, maybe I'll read off a couple of those as the questions come in. So Christian asked very early on about this problem that you did talk about, where high resolution means you start resolving less predictable phenomena, and then you need ensembles. And you talked about ensembles, Charmaine. But I think Christian wanted to ask how you balance these two needs of, I think, maybe affordability in the ensembles versus the certainty you get from resolving those processes.
Yeah, it's a good question. And I mean, if we could simulate, if we had, infinite compute power, we would just sort of be running, if you like, 100-meter ensemble simulations. I think this is very much part of the research that's going to be happening both for the RDP and the work we're doing. The MORUSES are also looking at this, as well as many other modelling groups around the world that are pushing down to these 1 to 200-meter type scales for their next generation of numerical weather prediction models. I think there are some phenomena, like if you're simulating urban heat waves, you don't so much need that ensemble approach. For convection, though, we often see that that's much more unpredictable, and that an ensemble system is really beneficial for that work. I think, first of all, the focus really is improving the models and the representation of the urban meteorology. That's a big focus. And then I think for us after that, it will be what is the best way to provide this information. And that may mean, going to a 300-meter model and slightly backing off in the resolution and being able to produce small ensemble potentially.
Yep. Rob Warren wanted to, I think, clarify about the particular tornado case for South Australia, saying that my understanding was that real tornadoes were associated with supercell thunderstorms, whereas those vortices appeared to be associated with shear instability along the convergence line. Yep.
Okay, so I'm just starting to look at the details, I guess, behind the tornado genesis in that simulation to see really what the mechanisms are. I mean, I think in terms of the features of the tornadic supercell, it looks pretty good. We do know from the few other simulations that people have done around the world at 100 meters, and some people actually have pushed down to 50 meters for simulations of tornadoes, that the model actually seems to over-predict the formation of the tornadoes, and also over-predict the strength of the tornadoes as well. So yes, it's not perfect in terms of its simulations, but I think as we start pushing to these high resolutions, there's going to be a lot more research done on really how they are represented in the model. Of course, it's kind of problematic that we don't have, the observations, of course, that we need to be able to look at the processes.
Mm-hmm. Yep. So Craig's put in a question. For a 2-week forecast, it seems unreasonable to spend up to 1 hour on data assimilation. For a 30-minute forecast, not so much. What sort of data assimilation schedules are being suggested for the Paris 2024 project?
Yeah, actually, no one's buying in yet to doing the DA.
Okay.
I think there are a few people talking about it. I mean, there are, at the moment we're kind of, I think the high priority is on, people doing ensemble simulations, if possible. I think part of the observational campaign next year, I think will help with getting those observations and maybe having people think about doing some DA approaches. In terms of operational systems, I know the METOFers are a long way from thinking about including DA. So they currently run a 300-meter model over London. They're looking at pushing that down to 100 meters. But DA, they're not even thinking about including that until 2028.
So where is the initialization coming from then? Is that from a 1 kilometer, 2 kilometer analysis, or where the DA must be being done at some resolution? What is that resolution?
Yeah, so that's coming from the 1.5 kilometer model.
Okay, and that's 3D VAR?
So it depends. So I think at the METOFers it's 3D VAR, but I think at the Bureau we're doing 4D VAR for our convector scale.
Okay, and the length of the data assimilation window?
1 hour, 30 minutes, one of those.
Right, okay. Okay, thanks.
Oh, fascinating. So it's the observations are purely for verification and sort of analysis.
At this stage, I mean, I think people are interested in having a go at the DA, but I think that's secondary. So where we are now, it's very much just getting the model set up, trying to produce a good representation of things over Paris. And then I think we'll probably, some groups will start looking at doing the DA. It's not something that we'll be doing for the Paris RDP, but it would be great if some of those groups did do that.
So one more question. How long, so suppose you start, you initialize the model at 1.5 kilometer resolution. How long does it take for the model to sort of build in these 100 meter resolution features? Does that happen in like 30 minutes or does it take a few hours or?
Yeah, so it depends, and it also depends. So often we have an intermediate nest, if you like, to help with the spin up of those features as well. So you might have this sort of 300 meter grid in there as well. And so depending on the meteorology, it can take up to an hour or so to spin up those features. So you do need to, I guess with all of these simulations, you do need to have quite a long spin up phase, if you like, before you start looking at the details of the simulations.
Mm-hmm. I had a brief question. We've got probably one more minute, but my question was about the direction of urban scale modelling. Do you think that this is going to become a priority for meteorological centres, operational meteorological centres, to start predicting city weather better?
Yeah, absolutely. I think so the WMO are very much pushing it, particularly in sort of developing countries where even more of their population is sort of based in those mega cities, in the urban areas, and they really do have issues around air quality and things that we're fortunate enough that we don't tend to have. So there is a lot of push to developing these systems. I think everybody wants to have more localised information, both for weather and climate. So I sort of see that this is going to, this sort of urban modelling work will only build in the future. Initially for us at the Bureau, it's going to be around developing systems for weather prediction. But I think once we've kind of got a handle on setting up these systems and we're getting some good results, there's a lot of interest in using them for doing climate projections and producing sort of that climate information. Of course, super expensive to run climate prediction at 100 metre resolution, but I think that the demand for this high resolution sort of modelling system is only going to grow.
Yeah. Thanks, Charmaine. Well, there is a couple more questions that have just popped up in the chat, but it's now 11 o'clock, so perhaps I'll ask you guys to ask Charmaine offline. But yeah, I wanted to thank Charmaine again on behalf of everyone at CLEX for giving this fascinating talk, and also invite the ECRs and postdocs to join me and Charmaine for a Q&A session purely just for ECRs from now, following the Zoom link that I sent around early this morning. So thanks everyone, and thanks Charmaine.